Hey everybody, I want to do a quick presentation about modeling populations, and I need to switch this. Quick demonstration or presentation about modeling populations, and this is sort of an extension of what we did last time in the little sort of lab exercise where you were estimating population. So with this sort of extension, take these population estimations, and you may do this through time. So say maybe several different years, and you start getting an idea of what the population is, whether or not it is increasing or decreasing. But you might want to know, based on these changes, what the population will do instead of 2 or 3 years, maybe in 10 or 15 or 20 years. And so these modeling exercises or modeling these models that allow us to look at these population changes through time is what we're going to take a look at now. So to start with, we need to define a population. And a population is a group of organisms, all of the same species, that live together. That live together and reproduce. And together is in parentheses there because there are sort of examples where organisms may not be together during a certain part of the year, and so they come together to reproduce. And you can think of some other examples probably where they're spatially or temporally separated. And then reproduce, we're typically talking about, in this example, or these examples, thinking about sexual reproduction, but you can think also about asexual reproduction as well. So populations change in their size by adding or losing individuals, right? So if this is our population, and we may add or lose individuals. Individuals are born or they die. And then we also have situations where individuals will either immigrate or emigrate. And when we're talking about these population models, population size is always designated by the letter N, capital N, where N sub t is the population size at time t, and then N sub t plus 1 is the population size at time t plus 1. In other words, the next time interval. And so we can look at this simply in this way, where the population at the next time interval, so next year, would be this year's population. So let me start over to the population next year would be equal to the population this year plus births minus deaths plus immigration minus immigration, right? So that's pretty simple. And let's assume that the population is closed. In other words, and we talked about this a little bit with the estimating populations, that you have to assume that no immigration or immigration. But let's assume the population is closed, and in that case, there's no immigration or immigration. And therefore, the change in population is equal to births minus deaths. And so we can take a look at an exponential population growth rate, where we look at the change in time, or I'm sorry, change in the population over the change in time is equal to a rate of change times the population, okay? And so that's the exponential population growth rate. And if we have an R that is greater than 0, you look and you see a curve that looks something like this with an exponential growth rate. And if you see an R that is less than 0, you see a curve that looks something like this. Now, I will say that this curve never reaches 0, but once you get below 1, then you can assume that the population is extinct. So moving on to projecting population sizes, okay, and we're going to take a look first at instantaneous or continuous population growth, okay, and you can think about the populations growing continuously and instantaneously. And this is the equation, okay, and I know it can look a little intimidating. Don't worry so much about that. So the population at the next time period is equal to n sub 0, okay, the population at a given time is equal to the initial population, or n sub 0, times Euler's number, which is this designated by E, and this is simply the base of the natural logarithm, which is equal to 2.781. All of that is raised to a rate of increase or decrease and time, okay? So there are some assumptions with this model, and this assumes that there's continuous growth. There's a growth with no time lags, where individuals are born and die continuously. There's no age or size structure. In other words, births and deaths occur equally regardless of age or body size. There's no genetic structure. In other words, there's no genetic variation. All individuals have the same birth and death rates, and there's constant birth and death rates. In other words, there are unlimited resources. Now, you can imagine that most of these assumptions are never hold true, and so, but again, this is a sort of simple model and gets us started with modeling populations. So the next thing we want to take a look at is projecting population size and look at a discrete population growth rate. So in other words, instead of population growth rate growing continuously, now we're looking at time periods where there are sort of pulses of population growth rate. So this might be spring, where there are birds that are reproducing, or some organisms may reproduce twice a year, or maybe they reproduce every 10 years or something like that. So this is those discrete time periods. So we're looking at discrete population growth. And in this situation, we still have n sub t, right? So that's the population at a given time, and that's equal to lambda, okay? And lambda is the finite rate of increase. And essentially that means that if the population grows 30% from year 1 to year 2, lambda would be equal to 1.3. Okay, so it'd be like 1 plus the 30% or the 0.3. And you multiply that by a raise to the time that you're, the time period that you have and that you're interested in, and then multiplied by the population at the original time, or the original population at time 0. All of these models that we've looked at have been what are called deterministic models. In other words, they, the outcome of these models is determined exclusively by the inputs, and there's nothing that is left to chance. In other words, there's no environmental or demographic stochasticity or chance. So let's take a look. Okay, we're going to look at some Excel examples. All right. So to start with, I'll share this Excel file with you guys so you can take a look at it and play with it. I may have an exercise associated with it as well. So there are obviously a lot of numbers here. We're gonna key in on a few. So first is R. Remember that and this population model is our exponential. It's our exponential continuous model. So that would be, again, the equation is n sub t is equal to n naught times Euler's number E raised to the rate times time. Okay, and so I can that's up here. You may see. There, so that's the formula built into Excel, and so you can see that if I change the rate R, and so this is, I should say, R here is equal to 0.02, and then 0.03 and 0.04. Okay, so those are the R values for each of these different populations, and you can see that the populations increase slightly differently, right? And you can see that in the figure over here. You also notice that this is the model, the mathematical equation, the model that we use to build these population projections, and for each of these. So you have 0.2, 0.3, and 0.4. So you can see that as the R value increases, so too does the rate of the rate of increase with the model, the population changes. If I change these, so for example, we'll stick with 0.2 here. We'll go to let's go 0.5, 0.0, 0.5, and then we can change this to 0.7. And you can see that they change more rapidly. So the bottom here we have, after 20 years, the first population with an R of 0.02 is 14.9. Then 27.2 and 40.6. Now, if I were to remove the 0, let's just do 3 and 4. You can see we get much more rapid changes in these upper, in the 0.4 than as compared to the 0.3 and 0.2. So after 20 years, with a 0.2 R value, we have 546 individuals. After, with the 0.3, we have 4,000 individuals, and then with the 0.4, we have nearly 30,000 individuals. All right, so that's the exponential continuous model. Next up is the exponential deterministic model. And if you were wondering earlier about Euler's number, and that is the log of the natural log of 1. Okay, so we can do exp, this is the equation, equals exp1. So I can say equals exp1, and it gives the Euler's number. Okay, so I just included that in there for you guys to see. And again, this time we're going to look at an R of 2, 3, and 4. Okay, and original population size is 10 across the board for each of these different populations. You can see that we have the formula is changed a little bit up here. And in this situation, we have the change is pretty rapid as well. As you get into 0.2, 0.3 to 0.4, the change between those can be pretty dramatic. Not as dramatic as in the last example, but you'll notice that in this example, remember that this is a model that looks at discrete time periods, whereas previously the model that we used, the mathematical formula or model, was for continuous population growth. All right. So I'll share this with you. You can take a look at it. Let's take a look at some other examples real quick. All right, so I have to do this. All right, so of course it is not that simple. So the idea of things there being no chance is typically never the case in nature, and so there is stochasticity or unpredictability that comes into play, and we can build that into the models. So forms of stochasticity that may affect populations are demographic stochasticity. In other words, individuals reproduce as integers and not continuously. So for example, birds might lay 3 to 4 eggs, but not 3.3 eggs. Okay, so and there are changes that can be built into these models where you model that stochasticity and model the random effect there. And then also environmental stochasticity. And there is certainly a lot of uncertainty in the environment. There are times where organisms might need water levels at a certain level, and there's either flooding or there are droughts where temperatures don't match up to their current needs, where there is another organism that may have a boom that causes that competes with the organism that's trying to reproduce. There's tons of environmental stochasticity as well, and so it makes it much more difficult to predict. So let's take a look at some examples with stochasticity built in. All right, so to start with, we're going to start again with a mean population. Our initial population is 10. And in this situation, I want to talk about real quickly this stochastic birth rate. Okay, and so you can see that we can use this formula, which is critical binomial function. And in this formula, you have to do the number of trials, the probability of success, and a random number between 0 and 1. And so, for example, in our birth rate, we say the mean, or there are 10 trials in the previous time period. In other words, there are 10 individuals that could reproduce, 10 opportunities, if you will. And the mean birth rate is 0.3. And then the formula builds in this random number generator that generates a random number between 0 and 1. And so that is the sort of the probability that's associated with that. Okay, and so you can see, for example, there were 10 individuals that could have reproduced. There were 4 individuals that actually reproduced, right? And the mean is birth rate is 0.3. So, and then in our death, we have the same formula here. And so instead of having 0.3, we have 0.1. And here, the mean death rate is listed as C2, and then D5, which you can't see, is actually the number of individuals in the last generation, that was 10 for this example. So there are 10 individuals that could have died, and in this example, there were 0 individuals that died. And you notice that every time because of the random number generator, every time I highlight a cell or open a cell to be able to modify it, and if I hit enter, that the values change slightly. So again, now we have 1 individual that died. And that's because of the random number generator. In this example, this n, so n underscore st is the stochastic example. Okay, so the stochastic population increase. So that's where we have that variability built into the model. Okay, and then in the deterministic model, that's simply the model that we used previously. And so this will always remain the same. This is the model that starts to change. So if you look at this curve, this blue curve will remain constant throughout any of the simulations that we run. And speaking of simulations, you'll see here simulations 1 through 22, and there's the stochastic simulations. This is the population estimate from each of the runs. You can see that the deterministic model always has 383 individuals, so there's 0 standard deviation. The average is 383. But when we look at the stochastic model, you can see that it will change every time this number here after 20 years changes every time we rerun the model. So it is currently 257, but if I rerun the model, it changed to 497. Right, and you can see that changes. So essentially what this is, this simulation, I would have changed this number to 497 and done that 22 different times and recorded each one essentially. And so then the deterministic model again has this constant value. All right, so that's demographic stochasticity. So we're talking about births and deaths. And then we also have environmental stochasticity. And in this situation, we again start to build in some of that variability. Instead of using the crit binom function, in this example we use the norm inverse function. And here we start with a random number between 0 and 1, the mean of the distribution, and the standard deviation. So in this first birth example, the random number is between 0 and 1. You see that here. And then the mean of the distribution is shown here as 0.0 or 0.6 underneath B. That's the mean births, and then the standard deviation that we built in here is 0.2. Right, and so if I hit go, you can see again it changes over here. In this example, I included 2 different stochastic populations: stochastic population 1, stochastic population 2. And then you can see these are the simulations, of course, again. And so you can see these things change through time. And then I also did this deterministic model. Again, the deterministic model always ends in 383 because we started with 10 individuals and these have these rates. Now I can change these different rates. So for example, if I changed the mean mean birth rate to 0.7 and change the mean death rate to 0.4 or 0.5, and you can see that we get these values start to change. Now, I'll also say that because of the model, this deterministic model here didn't change with these other values because I didn't build it in that way. So that model is always going to end in 383. But you can see when you start to add in these stochasticity, you start seeing a lot of changes in the final number, and so you get a lot of fluctuation as you take a look along these curves. All right, so let's go back to our PowerPoint presentation one more time. Oops, that's not what I meant to do. Let's see. All right, so now let me switch this. All right, so now we need to talk about resource limitations. So as you know, the resources are never limitless. There's always going to be some amount of resource limitation. And so we have to now start thinking about a different model. And this is a logistic population growth model. And in this situation, we're going to look at the discrete model. And so this is the equation here, and this is n sub t plus 1, where again, that's the population at the next time interval, where n sub t is the population at a given time, plus the rate R sub d, so that's the discrete rate or discrete growth factor, and then again n sub t, and that is all as multiplied by 1 minus n sub t over k. And k is the carrying capacity, and the carrying capacity is the maximum population size that can be supported, and that is limited by resources such as food, space, shelter, etc. So you end up with a curve that looks something like this, sort of an S-shaped curve or sigmoid-shaped curve that that is determined by the carrying capacity. So this population grew pretty rapidly, and it started to slow down as it approached the carrying capacity, and then it did not exceed that carrying capacity, right? So this is also a deterministic model, and let's take a look at some examples of deterministic models with that are logistic. All right, so in this example, we have an initial population of 2, birth and death rates, carrying capacity is 300, and you can see how the carrying capacity was calculated. It's the birth rate minus the death rate divided by the this A value plus the C value, and then you can see our rate is 0.6, right? Now, I want to point out that in the equation, the 1 minus n sub t over k is looking at what percentage of the carrying capacity has been used or is available. So, for example, when there are 2 individuals, we have used up less than 1% of the total carrying capacity, okay? And so then when we get to 3, there's about 1% of the total carrying capacity. And that obviously changes as you go along and add individuals, right? Where eventually you get to the point where you have, well, I should say, actually up here, where we reach, essentially here, where we reach 300 individuals, and that is the carrying capacity. So we cannot exceed that carrying capacity. And then if I change, for example, this birth rates from 0.7 to let's say 0.3, and you can see that it changes. And in this example, the 50 years was never enough to reach our carrying capacity. Or I'm sorry, it was, because our carrying capacity changed to 100. So our carrying capacity changed, and we reached 100 individuals around 46 years. Okay, so this is, again, a deterministic model. Next, let's take a look at and I'm not going to go through these in as much detail, but I want you to be aware that we can build in demographic stochasticity into these log models as well. So, for example, in this example, we have a carrying capacity of 1,000. I can change that a little bit to 1,500, and you can see when I did that the population increases, and it's sort of a little bit variable in this area, but it really changes in this area, really a lot of variability in this area here once we reach the carrying capacity. Now, remember that our carrying capacity is 1,500, so you can imagine a line that runs across here. You can see that maybe at least once we exceeded our carrying capacity, and this is typical of populations because they don't know what their carrying capacity is, so they'll exceed their carrying capacity and then drop down below, and then they'll come up again and maybe meet the carrying capacity, maybe exceed it again, et cetera, right? And so that is when we look at demographic stochasticity, here's an example where we're looking at environmental stochasticity, and in this situation, there are several different examples. This is where R is changed, is variable. This is an example where the carrying capacity is variable. In this example, this is where R and K are varied. And then there are also time lags. So we can build in where a population may exceed its carrying capacity, but it doesn't know it, and there's some time period before it crashes and drops below, etc. And then lastly is this sort of chaos theory, and you can see where there are these increases in population, and then it fluctuates up and down past the carrying capacity, and then it sort of levels out. And there are other examples where the carrying capacity is exceeded multiple times, up and down. Then there's this more stochastic example, and then this further sort of chaotic example down here. All right, so that's it for taking a look at populations, modeling populations, and I'll look for another, like I said, a follow-up exercise related to this. And let me know if you have any questions. I know this can be a little intimidating with some of the math. I don't think the questions that I'll pose to you will be too bad, so take a look at it, talk to your classmates via the discussion spaces, and we'll see you here again sometime soon.